Hello and welcome to another video. In this video we're going to be working on Parallel Courses 3. So in this problem you're given an integer n which indicates there are n courses labeled 1 to n and a 2D array relations where you have a previous course and a next course, and that denotes that the previous course must be taken before next course. Furthermore, you're given a zero indexed array time where time indicates how many months it takes to complete the course. You must find the minimum number of months required to complete all the courses. Following these rules, you may start taking course at any time if the prereqs are met. The number of courses can be taken at the same time. You can take as many as you want. And return the minimum number of months needed to complete all the courses. Note the test cases are generated such that it's possible to complete every course. The graph is a directed acyclic graph. And so this is going to be very similar to a course schedule. So if you haven't done that, I definitely recommend you start with that. And I'll link it in the description. I have a video for it. And you should be familiar with the cons topological sort. At least I've heard of it. If you haven't seen it at all, or you haven't done course schedule, I definitely start with that because this is essentially course schedule with add-ons to it. And so course schedule is a really common problem, and I would start there. But let's get into this one. So you have input 3, and here are your relations, right? So 1 needs to be taken before 3. And 2 needs to be taken before 3, and here's all the times. So essentially, notice how the reason this is 8 is because both courses need to be done, right? Both of these need to be done, and the limiting factor for the prereqs for a course is the one that takes the longest, right? So even though this one takes 2 months, this one takes 3 months, so you have to wait for both of them to be done. So the limiting factor for a course is the longest course. So the prereqs here take 3 because you can take them concurrently. And then here this takes 5, so it's 8 total. Now let's kind of use that same logic to figure out this one without even looking at this stuff. So these courses take 1 and 2 months. So the limiting factor for the prereqs of this, at least one of them, or actually not really, right? So let's look for the prereqs for 5. So there's 1 month, 2 months, and 3 months. These are all taken at the same time. And the longest one will be done at 3 months. So this has to be done. So this is 3 months. Then you have to take 4 before 5 as well, right? So this is the longest. You can almost think about it as what's the longest path to get to the end? And that'll be our answer. So because these are done at the same time, we need to see which one takes the longest because these are all prereqs. And so the longest prereq is actually 4, so we need 4 to finish first. So this is going to take 3 months, 4 months, and 5 months. So this is 12 together. So essentially, to summarize, for a course, the time it takes to complete the prereqs for that course to be available, right? For that course to be available is max of all the prereqs, right? You can take them at the same time, most of the time, unless they depend on each other, but assuming they don't, the time it takes is the maximum of all these prereqs. So you could figure out for each course what are the prereqs and what's the max and all these things. But let's kind of remind ourselves how a topological sort works to begin with, and then we can get a better solution. So for topological sort, let's just say we have a bunch of courses, right? So just say we have and we'll draw it as a graph for now. So let's say we have course 0 needed for course 1, maybe course 2 is needed for course 1 is needed for course 3 is needed for course 4, and then maybe we have course 5 that isn't, that doesn't need anything. And we are only going to draw valid solutions, right? Because they said all of the solutions will be valid, so we don't have to worry about cycles or anything. So that's all fine. So essentially, what we need to do here, and let's say there are times here. Let's say this takes 5, this takes 8, this takes 7 or whatever, 5, 8, whatever, 3, 2. So essentially, for a course, ideally we'd want to figure out how long it takes to complete the course starting at the beginning, and that's what we're going to focus on, right? So let's kind of go through that. For every course, let's figure out how long it takes to complete the course starting from 0, and then the one that's completed last will be the duration for all the courses, and that makes sense, right? You're going to take all these courses, and the one that you complete at the very end will be the duration. So let's go through that. So this will be done at 5, right? So this is done at 5. This is done at 8. All these prereqs are done as long as however long they take. This one's done at 5. Okay, now these actually have prereqs, so these are going to be like a little bit trickier, right? So this course relies on 2 prereqs. So let's take a look at that. So this course relies on these 2 prereqs. Which one is longer? It's this one over here, right? So for this course to finish, it needs both the prereqs to finish. They're going to take 8 because you can take them at the same time. And this course also takes 8. So for this course to finish, it's going to take 8 plus 8, which will be 16. Then for this course to finish, it has a prereq of this one. So for this course to finish, it needs to be 16 plus 3. So this will be done at 19. And then this course has a prereq of this one. And to get here, it takes 19 plus it also takes 2. So everything will take 21, right? 21 is the longest time to finish any course, and that's going to be our answer. So the tricky part to this problem is like, right, for a const topological sort, you want to take every course that has no in degrees. You want to take every course that doesn't have any edges to it and start with those, right? So you want to start with like this one, and this one, and then get rid of edges and then do stuff. But how do we kind of apply const topological sort, and how do we figure out, like, for this one, how do we figure out, okay, well, we can figure out when its in degrees is 0, but how do we ensure that we keep the right time to finish the course, right? Because for a normal const topological sort, you can use a stack, you can use whatever, because the order doesn't matter. You're just kind of trying to see, like, can I get it done or not? But in this case, you're not trying to see, can I get it done? You're trying to find the actual fast, or I guess, like, how long it takes, or not the fastest, but just how long it takes. So the way we're going to do this is we are actually going to structure our nodes. Instead of using a stack, we're going to use a min heap, and we're going to start the same way with all the courses that have no like nodes to them. And by using a min heap, essentially we will pop nodes that are available from the min heap, and essentially what will happen then is this one will finish before this one because we're using a min heap. And then that way, when this one finishes, the in degree for this will be 0, right? So when this one finishes, then one will be available, and then we can actually properly get the time by ensuring that for all the prereqs for a course, the one that takes the longest will finish last, and that way we can accurately keep track of the time. So let's kind of like walk through how this will look essentially with a topological sort example. So let's go back here. And we're still going to keep all the times, but let's just like have something like this. There we go. Okay. So I'm just going to draw these as nodes, but obviously we're going to represent these with in degrees. Actually, we could have this with in degrees, right? So we'll have nodes 0 through 5, and we'll have some in degrees and times, right? So for in degrees, 0 has an in degree of 0, 1 has an in degree of 2, 2 has an in degree of 1, 3 has an in degree of 1, 4 has an in degree of 1. I think this is correct, right? And 5 has an in degree of 0. Okay, so there we go. So these are all of our in degrees, right? And we can even like index them. So 0, 1, 2, 3, 4, 5. There we go. So we have our in degrees. And now we need to figure out like what goes where, right, essentially. And so let's do that. So we're going to have a min heap, and we're going to put everything with an in degree of 0 into the min heap, but we're going to sort it by the length it takes, right? So these two things have an in degree of 0, right? Node 2 should also have an in degree of 0. Yeah. So node 2 has an in degree of 0 as well, right? There are no edges coming to it. So for our min heap, what we're going to have is we're going to have the length it takes to finish and the node. So our 3 nodes are 0, 2, and 5. So 0 and 5 are both the same. So we're going to have, let's say, 5, 0, 5, 2, and then we have one more node, right? We have, actually, sorry, it's going to be 5, 0, 5, 5. There we go. And then 8, 2. So essentially, our min heap is going to be in the format of time and the node, right? So for like 0, it takes 5 to finish. For 5, it takes 5 to finish. And for 2, it has 8 to finish. And the order of these doesn't matter, right? If it's the same, it doesn't matter. So what's going to happen here is we are first going to pop 5, right? We're going to pop 5. So this is node 0, and it takes 5 to finish. Then we're going to go through all of the children for node 0, and we're going to lower the in degree by 1. So in this case, node 1, we're going to lower that in degree by 1, so that's going to be 1 now. And if there are any children with no in degrees, then we will add it to the heap. In this case, there are none. So we're just going to get rid of this node, and we are done. And we are just going to keep track of like the time it takes for the very last node to finish, because for a min heap, the very last node is going to be the longest, right? So we're going to go through this second node now. So 5, 5, we're going to pop it. So it's going to be node 5, time is 5. And we're going to see, are there any children? There are not. Right, so we're just going to get rid of that node. There are no in degrees or anything, so we're done with that one. Okay, now for 8, 2, so this is time 8, node 2, and 2 does have an in degree to node 1, so we will lower that to 0. Lower that to 0, and then what should the time be for node 1 once we add it to the heap? So it's going to be whatever it was for time 2 plus however 1 takes to finish, right? So 2 took 8, and then 1 also takes 8. So it's going to be basically the time for like to get here, and then the time for the actual course, right? The time to get to the course, and then for the time for the course to be done. So we're going to pop this, and now we're going to add, I'll essentially write a new heap down here. We're going to add node 1 with a time of 16, right? Because 2 took 8, and then 1 takes 8 as well. So we add 1 in here. Now we pop 1. So that's going to be time 16, node 1. And what's going to happen here is we're going to get rid of all of the edges from 1. So this edge to 3 goes away. So 3 has 0 now. And then how long should it take for 3 to finish? Well, whatever it was for node 1 to finish, which was 16, right? It's the time for 1 and the time for 2 together. So node 1 is done at 16 because we take that time from the heap. And then how long should 3 take to finish? Whatever it took to get there plus the 3. So that'll be 16 plus 3. So that's going to be 19. So we need to add into this heap, and then we popped this from the heap. Right, so this is gone. So now our new heap will be 19, 3. And then we need to pop that from the heap. So let's go back up here and finally get rid of this in degree. This is in degree 0 now. So remember, this took 19 to finish total. So it took 19. So how long should 4 take to finish? Well, 19 plus 2, so 21. So finally, we come down here. We have this heap of 19, 3 that we popped. And then we put in 4, which is 21, 4. And then that's the last node in our heap, right? So we pop that. That's the last node. And this 21 is our result, right? Whatever the last node is, we're just going to keep updating our result to whatever the time was for the longest time. Because that makes sense, right? Like if you take a bunch of courses, how long does it take for you to finish all the courses? Well, you can just figure out like how long did it take me to finish the last one from 0, and that's the total. So that's essentially what we're doing, is we're just adding time. And let's make sure that's correct. So let's actually go back here, let's redraw these paths, and let's figure out, was that actually correct? So here was our original structure. So obviously the longest path here is going to be this, right? This is going to be the longest. So this is 8 plus 8, which is 16, plus 5, which is 21. So that is correct. That's essentially what we're doing. We are doing a const topological sort, except instead of using a stack or a queue, we are using a heap. That way we're ensuring that the longest prereq is done last, and then that way our times for every node will be correct, and then the time it takes to finish the last node will be our result. And that's pretty much it. So let's code that up now. So we're going to have edges, just like a normal topological sort. We're going to have in degrees, 0 times n, right? We have n nodes. And because these nodes are 1 labeled, we're actually going to subtract 1 from everything. So we're going to say for parent, child in relations, because these are 1 labeled, we're going to make them 0 labeled. So we'll just say edges parent minus 1, append child minus 1, right? So essentially, we're going to have a dictionary of nodes and all of their children, but they will be 0 indexed now to make it easier. So we will have in degrees here, child minus 1 plus equals 1, right? So we get all our in degrees. Then we're going to make our heap. So we're just going to say our courses heap. We're going to do a list comprehension here, equals, and then we'll just use tuples for all of our elements in the heap. So remember, it's going to be time and the index for I in degree in, and then we can just do an enumerate here. in degrees. So remember, this is index and value, but we don't really need the value, right? We're just going to use the value to check if we're going to use it. So if the in degree equals 0, then we want the index and the time as well. So now we're going to have this like heap, but it's not going to be a heap, it's going to be an array. So now we need to heapify it, right? So heapify, and now our courses are going to be in order, well, not completely sorted order, but in order. And then we'll just say like result equals 0 or something. It doesn't really matter, right? We're just going to keep updating this result. So essentially, we heapified our courses. Now the course that is fastest to finish will come out first, and then our prereqs will come out in the order we want. So now we have while courses, and like I said, it's guaranteed to have a result, so we don't have to worry about like making sure there's a correct thing here. So we're going to say duration. We can't use time again because time is used. So in course equals heap hop courses, right? So this is how long the total duration of the course plus. Like this is how long it took to get here, to get to finishing this course. Then we're going to update our result to be whatever the last course we took was. Then we're going to check all the children in Edge's course. So we're going to check them all. We are going to decrement all their in degrees by 1, right? Normal topological sort. And if the in degrees is 0, then it's an available edge, or it's an available node, so we can use it. So if the in degrees is 0, let's heap push to courses. And this is going to be duration, right? However long it took here, plus the time for the course itself, right? So the time for the course itself is time child, and then the node is just child. And finally, we simply return result once we're done with this loop, because the end result is going to be the time it took to finish the last course, which is going to be the most out of all the heap because it's a min heap. So let's go and that. And yeah, this is basically a normal topological sort, but with a heap, and you can see it's very efficient. So let's go through the time and space for this one. So essentially, what do we have here? And let's look at our constraints as well. So our constraints looks like it's roughly like worst case scenario, it's like n squared or something. So it's definitely not like negligible. Like it could be greater than n, pretty much. Yeah, it could be greater than n, and then n is some big number. Okay, so to build our edges map, right, it's going to be, so worst case, every edge has an edge to every other, like every node has an edge to every other node, I guess, which would be like roughly n squared or something, right? Like they're showing here. But I guess worst case it is still 5 to the 10 to the negative fourth. So that's why this does get like this is fine, but essentially it would be somewhere along these lines of like n squared for actually getting the edges. Okay. And then for in degrees, that's going to be length n. So I think, yeah, this is going to be the worst part. This part's going to be n squared. But like I said, it can only be 5 times 10 to the fourth big, which is fine. For our courses, this is n, so that's fine, right? Yeah. But our edges can also be smaller. Our edges can be smaller than this, so we have to like keep in mind our edges and our nodes, I guess, right? So for courses, that's going to be, we do have to technically add this. So even though this is well, actually, no, it's less than or equal to. I guess worst case, yeah, worst case it's n squared, right? So worst case it's n squared. So I don't think we care about that, yeah, because if it's worst case n squared, this is basically irrelevant. The heapify time is n log n, which is also irrelevant, so it's just n squared. And then, so worst case scenario, we're gonna, or I guess not worst case, every scenario, we're gonna heap pop and heap push every single course, which would be n log n, but this n squared is worse, right? This part is worse. So yeah, I think it's just n squared because this is the part that takes the longest to actually make this dictionary of all the edges. Yeah, that part takes the longest because that can be n squared. Everything else is like n log n or n. So I think that's that. Now for the space. So yeah, the space is still going to be like n squared, right? So for every single node, it can have every other node, which would be n squared. Yeah. And then, as far as like the length of the heap and all that is going to be, the heap can be maximum every course, right? So that's going to be less, like all these. I think it's just going to be n squared, and n squared is our solution here. And yeah, it's going to be all for this one, I think. So hopefully you like this video. And yeah, I think it's a pretty reasonable problem. Definitely kind of like an easier hard problem, I'd say, once you recognize that like the order of the courses you need to take and you know const topological sort. Like if you don't know const topological sort, it's going to be very hard. But if you do know it and you can recognize it, it's not so bad. So yeah, it's going to be all for this one. And if you liked it, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.